So we can start now. Let me share my screen first. So good evening everyone, and welcome to week 7 of this live interaction session or doubt solving session for Matlab based programming lab in chemical engineering. So in this NPTEL course we learn Matlab programming, particularly focusing on use of Matlab programming to solve chemical engineering problem. And for this course I am your TA Bhavesh Moorjani, and every Tuesday we have this session for 2 hours, right, from 6 to 8 p.m., where I teach you some programming in Matlab. We solve some problems and understand our knowledge of Matlab, or evolve our knowledge of Matlab, right? So just brief about me. I have completed my bachelorates from MS University Vadodara, where I was introduced to this Matlab programming, and after that I was working at Gujarat State Fertilizer, and then I joined IIT Bombay as a PhD student. And in my research work also I involve use of Matlab for various analysis part, right? So that's why I have selected this course, so I can help you out in some way to understand Matlab in a better sense, right? So these are my socials. If you have any query related to specifically related to Matlab, obviously there are this live interaction session, you can come and discuss. Else you can post your queries through any such platform. I will try to reach out to you, right? So before beginning today's class, so let's briefly recall what we have done till now. So till now what we have done is we started from basics of Matlab. Before that we started, the first week was to understand the need of modeling, need of simulations, or need of programming language as a chemical engineer, right? Where we understand as a chemical engineer we solve multitudes of problems, multiple equations simultaneously, and every time it's not possible to solve these equations by hand, right? So in such scenario you have to rely on some software. It could be commercial software such as ASP.NET, DWSim, right, where you can do process planning simulations. There you have an advantage that you have inbuilt packages you can use directly. But let's say you are dealing with some small scale problems and you don't have such tool available, or you want more customization particularly for your problem. In such cases you can model your system or your process and code it out, right? For coding you can use any such language. Here we are using Matlab, right? So we understand the need of modeling and simulation, and then we move forward with the basics of Matlab for the second week. And then after that, from third week onwards, we have been trying to solve various chemical engineering problems. We have done problem of CSTR, we have done problem of plug flow reactor, right? We have done distillation problems. We try to solve various equations using inbuilt solvers, F solvers. Then we try to solve ordinary differential equation with initial value problems. So in that also we try to do the solution by the traditional numerical methods that we know, the basics method, and then we compared our result with the inbuilt function, which relies on same numerical method or the modification of that numerical method, right? So till now what we have done, we have looked at problems which mainly deals with the system of simultaneous equations. We have deal with the system with ordinary differential equation with initial value problems, and then there are some nonlinear equations in the fluid flow conditions that we have tried, right? So in today's class what I will do, I have selected out 4 problems which are based on the similar conditions that we have studied previously. So we will try to code, we will understand these problems and then we will try to code them out, right? So before beginning to today's class, I just want to point out what sir has taught in the week 7 part. So the week 7 involved unsteady state CSTR problem, right? And if you have been following my lectures, uh, then you will know that our previous session, which was week 6, we also solved the unsteady state CSTR problem, right? So here in this problem, sorry, yeah. you have been given two CSTR in series, right? And then you had basically you are looking at the initial conditions when you start the CSTR before the steady state has been is achieved in the in your system, right? So then when you write your mass balance and energy balance equation, since steady state has been not achieved, you have this differential term with respect to temperature, and your task was to understand how this concentration evolves with time, right? The concentration of A and B in both reactors with time, uh, and for that, so this since these are ordinary differential equations with initial value problem, you relied on ODE-45 or such other solvers to solve this equation simultaneously and find out the profile, right? That was the basic idea behind week 7 content taught by professor, and at the end you did some sensitivity analysis, right? So if you recall, the same thing we had done in week 6 class, which was previous session there also, but here we had only a single CSTR problem, which was kept at unsteady state. So we first tried to learn about what are different ODEs, ordinary differential equation, how we can categorize them, uh, the basics method to solve ODE inbuilt Matlab programs and how they differ from each other, right? And then we try to solve this unsteady state CSTR problem. So I'm just trying to correlate it that same kind of problem you might get in repetition. So uh, it's better to follow through this and code them so that you get more confidence, right? So if you had been following my lecture, then I think week 7 class would have been much easier for you to understand, right? So following the same analogy, in the today's class we will solve problems related to ODE differential equation and the system of simultaneous equation, right? So let's begin with the first problem. So first problem, we have again unsteady state CSTR problem, where the scenario is given that a complex reaction is taking place in the isothermal CSTR. So it's isothermal CSTR, temperature is constant. You have A plus B giving C, which is a desired product, and A plus C gives D. So here D is undesired side product. We don't want that. Now the reaction are elementary. What do you mean by elementary reaction? So elementary reaction will have the rate power dependence as a stoichiometric coefficient, right? So if I want to write the rate for first reaction, it will be K Ca to the power 1 into Cb to the power 1. For the elementary reaction, the power relation for rate expression is equivalent to your stoichiometric coefficient in the reaction, right? So that's why it's an elementary reaction, and you have been given rate constant for first and second reaction, okay? So that is liter per mole per minute. So it's this is a second order reaction, right? So that's why the unit is liter per mole per minute. Now the feed stream contains A and B with concentration Ca0 and Cb0 is given, both are 2 mole per liter, and a volumetric flow rate of 15 liter per minute. Now the reactor volume is given as 1000 liter, sorry not 1000, 100 liter, and the reactor is initially filled with pure solvent. All concentrations are 0. So if you will see, like initially when we start the reactor, so inside the reactor, okay, so since your feed has not entered, your product has been not formed, so that's why all the concentrations of the be the reactant, product or intermediate, initially at T equal to 0 will be 0. As soon as after T equal to T0, once the products or reactant starts coming into the reactor, you will get some value of reactant, some value of intermediate component, and some value of product. But before that, initially, since neither component has entered into the reactor, your all concentrations are considered 0. Okay, same logic was followed in the SIRS example also, right? Now the reactor startup is critical. Okay, so we have to simulate the first 60 minutes of the operation to understand how the concentration evolves. So we have been asked to plot concentration of A, B, C, D versus time, determine the time required uh, for the concentration of the desired product, which is C, to reach the maximum value, and what is the corresponding maximum value. Also we have been asked what is the yield of C at the maximum value, right? So yield is given as moles of C produced, like moles of your product created divided by moles of reactant consumed. Okay. So this is the this is the problem statement that we have been given. Now if we look for the unsteady state CSTR, and if you recall the previous lectures, then first step is, once you understand the problem, then we have to model that problem. We have to model that problem through our fundamental equations, right? So if you do the mass balance across the CSTR, right? So then since we have four components, we will have four component mass balance, and so this is how this component mass balance look like. Since A is taking part in both reaction 1 and 2, you will get dNA by dt, which is change in number of moles of A with respect to time, given as feed flow rate into concentration difference of Ca with respect to initial concentration, minus A consumed in the reaction 1, minus number of moles of A consumed in the reaction 2, right? Where Ra is given as your K1 CaCb, R2 is given as K2 CaCc. Right? So since it's an elementary reaction, it's second order reaction. Right? Now similarly, if you do the mass balance for B, C and D, this is how you should get the equations. Right? Since we have been following this equation for so long, I'm not going to derive these equations. If you have any doubt, you can try to solve them by pen and paper, right? So these are the four equations that we have to solve simultaneously to find the optimal profile. So once we understand the problem, we know what are the models governing the our system, right? We know how to solve them, since these are ordinary differential equations and these are initial value problems, right? Since we know the initially all the concentrations are 0 at t equal to 0. So these are initial value problems. So we will use ODE-IVP solvers such as ODE-45, the basic solvers that we start with, and then try to see how concentration of each component is changing with time. Right? So now the last part that is remaining is coding part. Has anyone joined? No. Okay. It's recording. It's taking longer time. It's open. Okay. So what we will do first, we will solve this problem into two parts. I will create the function which describes the governing equations, the mass balance equations for our unsteady state CSTR, and then in the main function, main code, we will call this function to solve this through ODE-45 solvers, right? So first, mass balance equation governing the CSTR operation. So it's a function. What we will get as the output of this function? So output of this function should be with respect to t and n, right? Okay. So let me name this function as CSTR ODE what are the information required for this function? So first, I am putting time here, although in this equation we won't be computing any data with time, but to solve this in ODE-45, we will also need the time part, right? So I am using time here. So this is just for the sake of consistency. So if you recall the previous lecture where I tried to put function in the ODE-45, since that function did not had a the time variable, it wasn't working. So to avoid that, what you do is you also insert this time variable or the independent variable in your function, so that when you are using this function, you are calling this function in ODE function, ODE-45 or any other differential solver. In that case, you don't get a discrepancy error, right? The other way around is that you describe or you create a function inline. So we create function with f is equal to @ your variables, and then you put equations. Okay, so both ways are possible, right? So just for the consistency part, you have to write it in a different format, right? So depending upon which method you use, your syntax will vary. Okay, so let's create this. So ODE CSTR. One thing, I will need a CSTR ODE. Then so one part is time. Then we need the feed flow rate, we need the volume, concentration of A, B, C and D is needed, right? And what else is needed? Yeah, K1 and K2 parameter is needed to find the rate, right? So let's say I call it N, which is my all the concentration part. So all the number vectors, the concentration vector for CA, CB, CC and CD, right? Then I need feed flow rate, volume, K1 and K2. So feed flow rate, volume, K1, K2. These are the rate constant, right? So this is my CSTR ODE. Now let's define all the function one by one. So first what we will do, extract concentrations from N. Okay, so here let's define CA as first component of N by volume. So my N vector, here the vector N that I am putting, I am considering it as a moles of component A, right? Moles of the given component. So that's why I am dividing by V. If you are considering it as direct concentration, that is also fine. Again, just a different approach, the different way to solve this problem, right? So N vector will contain all the information about the component concentration A, B, C, D. Okay, so you find the concentration, mole per volume, right? So this is mole per volume concentration that you have found. Now what else we need? We have to find the rate RA and R1 and R2. So my rate calculation, R1 is equal to your K1 into, you have CA into CB. Your rate 2 will be given as K2 into CA into CC, right? So here are the rate expression given. R1 is K1 times CA into CB, R2 is K2 times CA into CC. Okay, so we have computed both R1 and R2. Now I can put my ODEs here. Okay, let me call this variable as V is equal to CSTR or dc by dt. Dc by dt, this is a better term. So component balance ODEs. So first, dc by dt will contain the information for all the components, right? So first part will be the mass balance for A. Okay, So then you have F into delta Ca0 minus Ca. So F into Ca naught minus Ca. Okay, so one information which I haven't called is Ca naught. So I will also put Ca naught here, Fv comma Ca naught. So Ca naught is also called, minus you have R1 minus R2. Okay, so this is first ODE. Okay, then second ODE will be dc dt, second part, F into Cb naught minus Cb minus R1, since B is taking part only in the reaction 1. R1V. Okay, again. Volume is also there. I also need a Cb naught information. Okay, so Cb naught information is also given. Then dc dt, third equation is for your component C. So C is being produced in reaction 1, so R1 into V minus C is also being consumed in reaction 2. Okay, so this is how it equation will look like, R1V minus R2V, also minus FCCC, because it will also go along with the flow. So generation minus disappearance and then output. Yeah, so minus F into Cc. And then your last term, which is ODE for fourth component, your component D, minus F Cd. D is produced in the second reaction, right? So plus R2V, right? So all the equations are correct here, you can see. You can also put the comments that this is for Ca, this is for Cc and Cd. Okay, so output of this function, so what we call as a, what we ask for input as this, in this function is we ask for n, which contains the mole data for all four components. From that we find the concentration by dividing by it through the volume. This concentration we use to compute the rate. Both rate constants are called here. Initial concentration of A and B is also called, and then we get the four differential equations, right? So this will be our CSTR ODE. This is our function. Now let's create the main function to solve the unsteady state CSTR problem. Unsteady state CSTR problem. So always a good practice to remove previous variables, close all the previous files, right? Now given data for CSTR. So what information do we have? We have been given the initial concentration, feed flow rate and the volume. So we have Ca naught given as 2, right? Cb naught given as 2, feed flow rate given as 15, volume given as 100 liters, K1 is 0.1, K2 is 0.04, K1 is 0.1, K2 is 0.04, right? So this is K1, K2. I am not writing a comment. You can put a comment here to denote the unit. Remember, it's always a good practice to that you put a comments to either denote what your loop means, what your loop is doing. It's always a good practice to put a comment of units, right? As of now, this, since it's a practice problem and I have already tried it, so I'm not putting it, but it's a good idea to keep putting unit data, so that you know if you encounter any error, whether it's because of the unit conversion issues or not, right? So K1, K2, what else has been given? Yeah, we have to find simulate this CSTR for 60-minute operation, okay, from start to 60-minute time. So our time span, T span, it starts from 0 and it goes to till 60, okay. So this is my T span. Now solving CSTR ODEs to find concentration change time, okay. So I will have T comma N, it will be given as, I am using ODE-45, okay. So for ODE-45, first we have to provide a function. My function is CSTR ODEs, correct, T span. So my T span is this, y0 value, right? So y0 value initially, since we don't have any concentration, so all the initial concentrations, all the initial moles will be 0 0 0 0, right? So this is my CSTR ODE. Once this is done, what we have to do, we have to plot this data also, right? So for plotting, what we use, we have been asked to plot all the concentrations with time versus time, right? So once the ODE solves, extracting data from ODE result, okay. So my CA will become N by volume your CB will be second component, CC will be the third column, and CD will be your fourth column, okay. So this information we will extract out. Now how do I know this? Let's say I don't know what my CACEB will look like. So let me comment this and just run this part to see up to what point my code is correct or working, right? So I did this, I am getting some error which is ODE-45 CSTR ODE span. Yes, not enough arguments, because we call the CSTR ODE, but CSTR ODE also requires various input part which we did not provide it, right? So it requires T, it requires N, it requires flow rate, volume, K1, K2, CA0, CB0, right? Now let's see. Still we are getting some error. Unrecognized function variable T. Here let me put it as @ comma T comma N, and that's it. Just a minute. T comma, it's not T comma N. Now it should work. Error using ODE argument must return a column vector, okay. And what we are creating is a row, okay. Yeah, it requires a column vector. So let me create a column vector. No, this is my previous part. Week 7. What is different here? dn by dt. It has created zeros. So basically the this dc by dt, actually it should be a column vector. Let me rename it because it's dn by dt. So it's not appropriate. Dn by dt. And what I'm creating is I have created dn by dt as a column vector, since it was asking me that this function must return a column vector, right? So this is how I'm creating a column vector. And now let's call it. It has run it and it has created n and t data. So t contains time value from 0 to 60 minutes, right? The t span that we had provided. And corresponding n value, which are the moles, has been given here. Now it's mole. So in our equation, in our CSTR ODE, right, n1 correspond to A, n2 correspond to B, n3 correspond to C, and n4 correspond to D. Okay. So similarly here also, like the data that we are getting 1, 2, 3, 4 represents A, B, C, D value with time, right? So once you know that, so you extracting the information for concentration becomes easy part. That your CA will be all the row data for all the row data for column 1 divided by volume. This will become your concentration, right? Now you can plot them. Plot your time t versus CA, time t versus CB, T versus CC, T versus CD. X label is time in minute, Y label is concentration, this much mole per liter, right? What else we need? Legends, right? Legends. So it will be CA, CB, CC, and CD. Let's run it. You are getting this plot with all the data of, so how your concentration of A is changing, B is changing, C and D, right? So initially everything is 0. As soon as you start the CSTR, both A and B starts coming into the reactor, right? By the time it's filled, the reaction between A and B will also start, and you will get starting C. Now C also takes part into the undesired side reaction with A and creates a product D. Okay, so this will continue till your reaction achieves a steady state. Once your steady state is achieved, which appears to be somewhere around 30 minutes, after that you can see your all the concentrations are not varying too much, right? So somewhere around between 30 to 40 minutes your steady state has been achieved, right? And then after you get a constant profile. So this is how we see the variation. Now what has been asked to us? We have been asked that we have to plot the concentration with time, that we did. Determine the time taken for the concentration of desired product to reach the maximum value. And what is this maximum value? Now I have the data of CC. I have all the concentrations for C, right? So I can use the maximum command to find out the answer, right? So maximum concentration is 0.6360, but it corresponds to which time unit? I don't know, right? So for that, what you can do, you can modify the maximum command. Like here I can put the max C, put the index corresponding index IDX and run the command. So by this way, when you run the maximum command this way by providing the two input arguments, right, then you will get two values. First is the default value, which is your maximum value, and which index it corresponds to, right? So it corresponds to 101 index of CC vector. So in CC vector, if you will go to 101, you are getting 0.6360 mole per liter concentration, right? So this is your concentration. Now corresponding to it, what time I will have, so I can put time NDX. So for time I have used T, right? So T index 101, so that is 60 minutes. So at 60 minutes my concentration will reach the maximum value, I can say that, right? So same thing we can put it here, that this was part 1. Then your part 2 becomes finding the maximum concentration, right? So part 1 was plotting, part 2 will become finding maximum concentration of C. So for that, what I am using, max C value comma index is equal to max of CC, right? Once I know that, I can use fprintf command and say that maximum concentration of C is, let's say, %f at time t equal to %f, comma, so 1 is max C, put it capital. So max C gives you the maximum value, and corresponding time value will be T bracket your index. Okay. So this is the second part, and when you will run it, you will get answer in this sense, that maximum concentration of C is 0.6360. I have to put a unit, mole per liter, at time t equal to this much minute. So C is this much mole per liter at time t equal to this much minute, right? At the end you can put /n to start a new line. Okay. So that's what second part. Third part, we have been asked to find a corresponding yield at this point. Okay, so we have been asked what is the yield of C at given point, and yield is given as moles of C produced divided by moles of A consumed. Now I know maximum value is achieving at what time. Okay, I know the index, I know the maximum value, so I can find the yield of C. Let me call it as YC equal to moles of C produced, that is your maximum C value, right, divided by moles of A consumed. So A will be consumed, that will be Ca0 minus Ca value at your final index. Okay. And then you can print this, simply print this data, that yield of C is this much. This will become your YC and time index, and let's run it. So this is how you are getting a plot, and these are your result, that maximum C concentration is 0.6306 mole per liter, which is achieved at time t equal to 60 minutes, and at that time your yield of C is 0.648. This much, actually it will be fraction value, not this part, right? Okay. So this was the first example. What else? I think it was pretty straightforward, again kind of related to what we have done in the previous class and what sir has taught in the week 7 part. So it's kind of an extension to what you have already done it, so it's fairly simple. Now let's move forward with the second problem. Just give me a minute. So second problem is for multi-stage liquid-liquid extraction problem. What is the scenario? Scenario is given as we are removing a solute A from water using pure benzene as a solvent in a 3-stage counter-current liquid-liquid extraction cascade. Now the flow rate of water phase, which is considered as raffinate, is 100 kg per hour. The flow rate of benzene, which is extract, is 200 kg per hour. The inlet stream has a composition of XF is given as 0.20 kg of A per kg of water. The equilibrium relationship is linear, which is your Yn is equal to K into Xn star, right? Where the distribution coefficient value is also given as 0.8. Now Yn is your concentration or mole fraction of your solute in the extract phase, and Xn is your concentration or mole fraction of your solute in the raffinate phase, right? So its relation Yn by Xn is given as distribution coefficient value K. Here assume that water and benzene are immiscible, so they are not mixing with each other, so only the solute is getting transferred from between the extract and raffinate phase now. Okay, so what we have to do, we have to calculate the composition of solute in the raffinate and extract stream. Now if you will think about it, we kind of had dealt with the this kind of problem previously also, right? So this is a simple mass balance problem where you have multi stage mass balance that you have to do, right? And if you will think about it, this mass balance equations are nothing but a system of simultaneous equations, right? So right now we have not derived it, but if you know about liquid extraction, you know these are the linear problems. These are generally linear problems, right? So you have system of linear simultaneous equations, and to solve that, what we had done previously, we had done Gauss-Jacobi method. We relied on the inbuilt solvers such as LinSolve from the Matlab, LU decomposition methods to find the solution. So same strategy will be used here, but before moving to that part, we have to first understand what is the governing equations in this part, how we can model this particular problem, and then we will try to code it into the Matlab. Okay. So for this multi-stage LLE, if you talk about any, if you consider any n stage, right? Let me show you the LLE part. Multi-stage liquid extraction. Yeah, so this is how your multi-stage liquid extraction look like. So you have feed coming from one side, your solvent coming from another side, right? Since it's a counter current flow, this is how exactly it will look like. Your feed will come from one side, your solvent will come from the another side. Okay, for a given stage there will be exchange of solute between extract and raffinate. Then further your raffinate is forwarded it to the next stage, and your solute, which is considered a solvent, which is considered extract, which is in solute rich phase, is for it put forward, right? Okay, so this is how your schematic look like. Now here you have 3 stages. So at every stage you will have a mass balance, right? So for 3 stages you will have 3 mass balance equations. Okay. Now to solve them, let's first find out what this mass balance will look like. So first I will have one total energy balance, right? So if I consider any end stage, not energy balance, my mistake, mass balance, right? So now I will have total mass balance for a given stage. That will be your extract is coming from a previous stage, your raffinate is coming from the next stage. uh, that will be equal to your extract going out from the current stage minus raffinate going out from the current stage, right? So this is how it should look like. If I consider this example, extract is coming from the end stage, raffinate is n minus 2. Sorry, here the notations are different. Yeah. So for the n stage, let's say consider n minus 1 stage. So your output stream is En minus 1 and Rn minus 1. Okay. So similarly here also my output stream is En and Rn. Okay. So that is on the right hand side. My input stream here is En minus 1 and Rn plus 1. So I am considering that extract is coming from n minus 1 stage from this side and raffinate is coming from this side. Okay, so it's a different direction that I am considering. So if you will consider in reverse, your order will change, right? The notation will change. Okay, so if I considered here, the raffinate is coming from the previous stage and extract is coming from the next stage, but in my case I am using the different part, but that's fine. At the end the overall mass balance should not be affected by this. Then you will have a component balance. In component balance, what you will have, you will have extract which is coming from your previous stage, the concentration of a given component of into that stage, plus raffinate coming from the next stage into the concentration of that component in the raffinate will be equivalent to extract into Yn in plus raffinate into its concentration of component in the raffinate part. Now you also have the relation between the extract and raffinate mole fraction of a solute, right? So Yn by Xn is given as K, right? Now generally this K won't vary, so you can consider it as a constant for all these stages, right? You don't have to worry about it. Now if you rearrange this, so what I want to do is I want to do the component balance, and since here I only have a one solute, I want to do the component balance of that solute with respect to Xn only, right? Since I know the relation between Yn and Xn, you put Yn is equal to Kxn or Yn is equal to Yn minus 1 is equal to Kxn minus 1 in any equation and try to rearrange it. So all the equation after rearrangement are with respect to X, which is your raffinate composition, right? So this is how you are creating it. And then if you follow this method and do the component balance for it at each stage, right? So this is how you will get your data for each stage. If you have any doubt, do try it out also, okay? So let me just show you example for one stage. That at the first stage what I will have En minus 1. So 1 minus 1 is 0. I don't have any zeroth stage, but what I have corresponding to that stage is my feed, right? So I could write it as E, which is your extract 200 kg per hour. So E into K into XF value. Okay, so this is your feed inlet part, but since it's a constant value, you know it, I have taken it at the right hand side. Then at a given stage, stage number 1, x1 into you will have E1 times K plus R1, right? Now here I am considering the flow rate of extract and raffinate passing through all these stages is constant. So that's why I have gotten rid of En, Rn notations. Instead of that I am just writing E and R, okay? So that means it becomes equal for all cases. Then input from coming from the raffinate also from, so that is R into X2. So this is one part. Similarly for second stage you will get this equation. For third stage you will have X4 value. Now since X4 that is a raffinate coming from the raffinate coming from your that's actually your solvent coming from the fresh solvent that is coming, right? So in that case your x4 will be 0, so the last term here is not there, so you have only 3 stage and the corresponding composition x1, x2 and x3, right? X4 is 0, that's why the last term in the equation 3 or the stage 3 equation is 0. X0 becomes your xf, okay, so that is your value here, right? So this is how your scheme looks like. Now so we have 3 equations, 3 unknowns, right? So it's a unique system. We should get the unique solution, right? So let's try to code this, and let me just take out the previous code for a reference, right? So here it is, multi stage liquid extraction problem, right? Always start with removing previous variables, removing previous graphs, okay? Once that is done, did I change the name? I didn't. Okay. Now the given data, it says what information we have. We have the extract flow rate, which is 200 kg, raffinate 100, so even I'm considering extracting benzene, which is 200, and E into K into XF. Right. Yeah, no, I think it's correct, huh? So given data, your E is 200, R is 100, XF is given as 0.2, then you have K value is 0.8, what else, 100 to 0.8, right? Now creating coefficient matrix for solving the composition. So what kind of matrix we will have? Here we have coefficient matrix A, my composition vector X, and the constant vector B, right? So Ax equal to B. Now here my X that I have to find, right? X I have to find, my A matrix is, so what I will do, since I have 3 equations, 3 unknown, so it will be 3 by 3 matrix, right? So I will be creating a 0 vector with 3 by 3 matrix, right? So A has been created with size 3 by 3. Now for all the corresponding size, I will put the coefficient value. So A, here the 1 part which corresponds to x1 is given as minus ek plus r. So A 1 is equal to minus E into K plus R, right? A1 comma 2, which corresponds to the coefficient of x2, is given as R. A1 comma 3, coefficient of x3 is 0 here, right? So I don't have to provide it. Now moving on to second equation, the coefficient of x1 is E times K, so E into K. Coefficient of x2 in the second equation is negative minus ek plus r, and then coefficient of x3 is r, so a2 comma 3 is equal to r. And then moving on to third equation, now corresponding to x1 there is no coefficient, so it will be 0, so I don't have to provide it. Corresponding to x2 we will have positive E into K, so E into K, A33 is given as minus EK times R. Now my B matrix is so first value is right hand side is minus EK times XF, so minus E into K into XF comma 0 comma 0, right? So solving this simultaneous equations, my x becomes a by b, right? So I'm using this back division operator to solve the problem, right? And then what I will do, I will display x. I'm getting some error. XF, oh, it's capital X. Oh, I'm getting negative values. It should not happen. That means we made mistake somewhere. A by B zeros. Let me just quickly look the previous example. R100, E200, 0.8.2. Here it was working fine. If I display X here, it's all positive value. Just a minute. R minus EKR, EKR. Oh, the matrix I have chosen are it should be vector this way, not the row. Yeah, actually I was doing a wrong division here. Backslash operator I should use, right? And and I will get an error because dimensions are not agreeing. So here dimension should be, B should be a column vector, right? Column vector, and then run it. And this is your x1, x2, x3 value, right? Now this is x1, x2, x3 value. So you can find the corresponding y value. Your y matrix will be y is equal to k times x, right? You can display y also. So this is your x value, this is your y value at output of stage 1, stage 2 and stage 3, right? So it's again very pretty straightforward problem. You can write it into fprintf format to print all the data very nicely, right? Just verify the equation. Now I am doing it, I am just confused with this one equation part, en minus 1. So benzene I should refer here as solvent, so it should come in R, and this. Let me just quickly change this ENR notation and do it. Because your problem says water phase is 100 kg per hour, benzene, which is your solvent, is 200 kg. Now in your equation, extract, so this is feed is coming through water I'm calling it extract, which has a initially higher concentration, 200. Solvent side is called E. Here I'm just slightly confused about the site notation. Initially I didn't pay attention, right? See, the direction and of this feed and direction of your the solvent, they are opposite to each other, but the way you consider this equation is an important part, right? So I think here it should be the benzene phase, I think I was referring at as R, and the water phase as extract. Okay. So just confirm the notation. I am slightly confused here. So here in this, according to this diagram, feed is considered as raffinate, okay, so FRRR, and the solvent part is considered as extract, okay. So if we do that and try to put it, if I do mass balance according to this equation, extract is coming from the end stage and raffinate is from n minus 1. So in that case, this equation will change. So this I will leave up to you guys. Basically what I am saying is the direction that you considered for the extract and raffinate, which part you considered, just make sure that you are correct. I think here this should be reversed, that the way I have considered the equations, water will come into the E part, and the benzene, since it's a solute, it should come from the R part, the way I have considered the equation, right? Just do verify it one time, okay, by doing a proper mass balance. But the basic idea was that you will get this system of equations when you are solving the multi-component liquid-liquid extraction problem, and once you do that, you can solve this multi-component equations using inbuilt Matlab packages, right? I can also use, instead of A/B, I can use linsolve, right? If you remember linsolve, we have been previously using it. So anyway, you can use any such methods, whatever you prefer, and you can solve it. Just do verify the mass balance part, okay? Because of the timing, I'm not going into the detail of that. uh, okay, but it's important to know that your model correctly represents your system. Since it's a practical, it's just practice example, I'm not focusing on to that aspect. Then let's move forward with the third example, which is plug flow reactor with a pressure drop in the reactor, right? So for this part, one governing equation is your obviously the mass balance equations, which involves the reaction part. But here we have been also said that this time pressure drop is also occurring into the reactor. Then we have to be cautious, right? So what is the scenario that has been given? We have been given that you have a gas phase reaction where 2 moles of A are producing 1 mole of B, which is carried out in a plug flow reactor. Reaction is elementary with a rate constant K given as 0.05 liter mole per second. The feed is pure A with concentration of 0.5 mole per liter. Volumetric flow rate of feed is given. Initial pressure P0 is given. Reactor diameter is also provided. Now the reaction mixture viscosity is also given. Now the pressure drop in the reactor is significant and follows the Ergun equation. I will come to that part also. What is this Ergun equation? Consider the beta 0 as a constant for this problem, which is also part of this equation. Now what we have to model is the conversion and the pressure as a function of reactor volume till 500 liters we have to consider. So plot conversion versus P by P0 ratio, which is your pressure at a given point divided by P0 value versus reactor volume. Compare the exit concentration in case where pressure drop is neglected. Okay? Now till the previous problem, if you will recall, what the problem that we have dealt with CSTR or PFR, mostly they were liquid phase reaction. We were not worried about the volume change part, right? Whether it was mentioned explicitly or not, but we hadn't considered any volume change part. But here it has been mentioned that we have a gas phase reaction. We have 2 moles of A converting and creating 1 moles of A, and it's mentioned that your pressure is changing drastically, right? You can understand that your half a mole volume, half a mole are decreasing as your reaction is proceeding, right? So your pressure will be affected since you are in the gas phase, reaction. Okay, so in that case you have to also worry about the how the pressure change will also affect your reaction part. So when you will do the mass balance part, it will also involve the change in the pressure of your reactor, okay, or change in your volumetric flow rate. So for that we will do, first we will see how, which model we can use to represent our system. Okay, just give me a minute. Do we have anyone? No. Okay. Yeah, this is recording. So here, first let's look at the mass balance equation, right? It's plug flow. So for CSTR, when you will do the mass balance, this is the kind of equation that you will land up with, where you have change in the conversion of A, which is your reactant, with respect to volume, given as minus RA divided by feed molar flow rate, right? The initial flow rate, and your rate is given as, since it's an elementary reaction, it's given as minus Ka Ca square. Now since it's a gas phase reaction, there will be some volume change that will be occurring. Okay, now when volume change is occurring, so if you will do the ideal, if you equate the inlet and outlet with the ideal gas law, right? So in the ideal gas law, what you have PV is equal to nRT, right? Sorry. So in the ideal gas law, you have PV is equal to nRT, correct? Then if you divide both the side with time, then you will get P. Instead of volume, you will get the volumetric flow rate. Instead of moles, you will get the molar flow rate, right? So if you equate this at inlet and outlet, then you will get P0, which is at inlet, volumetric flow rate at inlet, is equal to your not equate, sorry, you have to take the ratio of P by V and RT, not N, F, sorry, F not RT divided by, it will be F R and T. Considering isothermal reaction, your temperature is going away, then you will have the volume, you can get the volume V in terms of V0, the ratio of your flow rate and ratio of the pressure, right? So this is how you will get the change in the volume. Okay, so this is how your volumetric flow rate is changing for a gas phase reaction, right? Now if you look at the Ft, which is your total flow rate, the mole flow rate, Ft here, you can also relate it with the conversion that is happening into the reaction, right? So Ft is equal to Ft0 into 1 minus, so it's given as actually Ft is equal to Ft0 into 1 minus dxa. So your D is your ratio of how much moles are changing in a reaction, right? So here from 2 moles you are going to 1 moles, right? So that's why D is half here. So your Ft is equal to Ft0 1 minus half a times Xa. Okay, so this is how your total molar flow rate is changing with time as your conversion is changing. Now initially, since you only have A, your FTO is equal to FA0. Now you have this two information. You have V with ratio of P0 by P and Ft by F0. Similarly, you have Ft in terms of FA0 through this equation. So when you want to find the concentration, because in my rate expression here, I have concentration Ca. Now previously my concentration Ca was either I was solving my ODE with respect to concentration Ca only, but this time my ODE is with respect to change in variation of mole fraction with respect to volume. Now mole fraction Xa, normally you can relate it as Ca 0 minus Ca divided by Ca0, but here your Ca is also varying. Your Ca is given as flow rate divided by volume. Now your volume is also not constant, it's varying with time, varying with the reaction. Okay, so that's why when you put V in terms of this equation, instead of Fa you put it Fa0 into 1 minus Xa, and you solve it, you simplify it, you will get concentration with respect to your pressure ratio and your initial concentration and conversion, right? So here normally when we write for a liquid phase reaction, we write Ca is equal to Ca0 1 minus Xa, but since it's a gas phase reaction, and that's why you have the ratio of P by P0 also coming into picture. Since volume is also changing, your flow rate is also changing, then that's why you have also secondary term, this 1 minus 0.5 times Xa. Okay? So again, if you go back to your reaction engineering part, in the reaction engineering you must have studied what this gas phase reaction, when you have a constant volume and you have changing volume part, right? So try to apply that fundamentals here, and then you will end up to this equation, right? So in my reaction part, which first ODE, which is change in conversion of A with respect to volume, I have a CA, I have rate term which includes CA, which I understand is from the modeling my PFR, that I get to know that it's also dependent on the pressure part. Now it has been known that pressure is also changing, so how to model that? So for packed bed reactor, the Ergun equation is used to find the pressure drop in the packed bed reactor, and that equation is given as change in value of P divided by with respect to change in the volume of V, dP by dV, as a ratio of your pressure ratio, temperature ratio, and the flow ratio. Now, since we are considering isothermal reaction, your T by T0 goes away, and then you are only left with P0 by B. You all know the relation between Ft by Ft naught. So this is this one, and this B0 term. Now, this B0 term is related to the property of packed bed. Okay, property of your packed bed or packing that you have. Okay, let me show you the example of Ergun model for packed bed reactor. Yeah. I will show you the glimpse only. You can refer to your engineering books to understand the equations much better, right? Now these equations are given in different forms. I think we are using the simplified form for the packed bed reaction. So this is how your Ergun equation looks like for the packed bed column. Okay, right? So you can see it's correlated on the various packing parameters, your porosity, your dP, your parameters, right? There is this other Ergun model. That's not loading. Yeah. So same Ergun model, pressure drop in the packed bed reactor. From this, if you simplify these equations for your system, you will end up with dP by dV this form. So it's change in the pressure with respect to weight of your catalyst, and then you have this alpha term, and these are the ratios that we were discussing about now. Now further, when you change from volume, you move from weight, when you move forward with the volume, you try to find the change in the pressure or the pressure drop with respect to change in the volume. Then you will end up with the beta equations that I have shown here. I don't think so they have it here. Just give me a minute. Okay. Yeah, it was at some place which I forgot. There was some reference, or you can refer to any engineering book problem which focuses on the design part. You will land up to this equation. I think, yeah, this one. Yes, here you can see the Ergun equation is modified. So here it's with respect to the length. You can consider it as a volume also, and this B0 parameter, it's related to your property of your packed bed, right? So it includes the packing factor and etc. Stuff here. So for our problem, what we will consider is, we have been given that we have to consider B as a constant value, right? So we don't worry about it, but in actual problem it will depend on your property of your system. So dP by dV is also given. So we have equations. So we have two equations here. One in change in the concentration with respect to volume, and another change in pressure with respect to volume. So we have two ODEs, and we know the initial conditions for these two ODEs, right? We know the initial P0 value, we know the initial conversion XA is equal to 0. So this becomes ordinary differential equation with initial value problems. So we have been dealing with this from past few lectures, right? So once we know, now we know the we understand our problem, we have modeled it, we know these are ODE-IVP problems, we know the solution strategy. So only part remaining is to code them, right? So let's do that. So for coding this, like the CSTR problem, what we will do, we will first create create the PFR ODs, which will represent the governing equations in our system, and then we will call it in the main function, right? So this is my change with respect to volume, right? So let me call it as dy by dv is equal to my PFR ODs. Okay, what input I required for PFR ODs? So I need the K value, I need the CA0 value, I need the P0 value. Okay, so there are multitudes of data required. So first my volume, obviously that will come. It's not taking part in into this function particularly, but when we will call it into the ODE part, we will need it. My variable y, so y will contain my XA and pressure. Okay, CA0 value I will need, then CA0 I will need FA0, P0, FA0, P0. What else we will need? And beta naught. Yeah, we will also need beta, B naught. Okay, ODEs representing PFR problem. Gas phase. Okay. Yeah. Now, first I will find the rate. Rate is given as, no, before rate, so I have to find first CA. And CA is given as CA0 1 minus XA P by P0 ratio, right? So let's take out the information first. Here I will say Y is my dependent variable matrix, right? So my CA will be y comma 1, my P value will be y comma 2. Okay. Once I extract out this information, what I will do is find the CA. So CA is given as CA naught into 1 minus XA. Sorry, this is XA. XA divided by 1 minus 0.5 times XA this whole into your P by P0, P by P naught, right? So this is your CA that you have computed. Now once CA is known, I can find the rate RA. So my RA becomes K1 into CA to the power 2. I will also need to call K1 from my equations, right? So B naught K1, let's say. So K1 is also called CA square. I find the rate RA. Now I can use it to find the first ODE part, which is minus RA divided by FA naught. So my dy by dv becomes minus RA divided by FA naught. Okay, so this is my first ODE. Now my second ODE is dp by dv is equal to minus beta 0 p naught by p into this factor. So maybe I can write it directly, dy by dv, second row first column, since I need a column vector, minus beta naught into p naught by p into 1 minus 0.5 times xa. Right. Yeah. So this creates your PFR ODs. Let me just quickly check with the previous one. I have CA, which I find it out. Find the RA. This beta p naught by p FD over this, and I can return dy by dv. Yeah. Okay. So this creates your PFR ODs. Now let's do that. Gas phase PFR reaction. Let's try to solve it. Here, what is the start with removing all the variables, closing all the previous graphs, clearing the screen. Now what is the given data? Given data is that you have FA naught K naught. So first is CA naught. CA naught is given as 0.5. FA naught is given as feed flow rate, yeah, 10 liter per second. This is V naught. V naught is your 10 liter per second. So V naught is given as 10 liter per second. Now your CA into V, CA naught into V naught, this will give you your molar flow rate, right? So this is liter per second, mole per liter. So multiplying this, you will get mole per second flow rate. Your P naught is given. P naught is 10. Then diameter is not needed, viscosity as of now not needed. Beta naught I need. Beta naught is given as 0.01, 0.01. Volume V. So we have to go to V max is equal to 500. So my V span will become, I will start from 0 to 500. Okay, so this is my V span. Now I know the ODEs, I know the initial variables. So we will solve it calling ODE function to solve PFR equations, right? So I will have volume vector versus this y vector, which will give me, I am calling ODE45 again, at the rate, my function is with respect to Vy, PFR ODEs For PFR ODs we need V, we need Y, we need CA naught, we need FA naught, we need P naught, K1 and comma B naught, right? K1 value I haven't specified, right? K1 is 0.05, right? 0.05. Now you have to provide the span, okay, and your initial value y0. So what is your y0? That is initial initial conversion and initial pressure value. So that I can write it as initial, there is no conversion, and initial pressure value is P naught, right? So it's P naught. And let me just run it quickly to see whether whatever we have done, it's working or not. It's running. Oh, yeah, sorry, one mistake I made here. This is a column vector. I keep forgetting it. Yes. So this one is column vector OD45VY. It's still running. It should not take this long. Just give me a minute. Oh, I made a mistake here in PFR OD. So RA is also minus KACA square, right? Here your rate minus RA is given as K1CA square, so it should be this way. Then now it should work. Yeah, it's running. It has completed the analysis, and you have the various volume values. Corresponding to that, you have conversion. You can see conversion is increasing and your pressure is decreasing. Okay, so your first objective is complete, but then you have to present it nicely. So what has been asked is plot the conversion X and normalize pressure P by P0 versus reactor volume. So we will extract out this data. Extracting solver data, right? Your XA becomes Y, all row, first column, your P becomes Y divided by second, all row, second column. Then your P ratio is nothing but your P by P naught. This is your P ratio. Now I want to plot it. So for plotting, what I will do, plot, we do volume versus XA, right? Let's call it as blue color. Then you have hold on, plot V versus your P ratio. Let me create a red line for this. My X label is volume in liter, my Y label, it will become conversion or ratio, and if I run it, I'm getting this plot, right? So here my conversion is increasing with the volume and P by P naught is decreasing, okay? But this I have plotted in one graph, right? Now I want to separate them. Now previously what we have done is, if I had a let's say if I had a multiple data points, then what we used to do, sorry, not multiple data points but multiple different values to be plotted, we will use subplot. So we will have one plot, we will plot it in same part, one plot representing some data, other plot representing some data. But let's say I want to see the change within one graph only, but that I cannot do, right? Here I have the conversion also and the pressure variation also. Now conversion is increasing from 0 to 0.5, while pressure is going down from 1 to 0.4. So they are at different scale, still closer. But let's say instead of P by P naught, I just wanted to see the P value. In that case, my P scale will be different, right? So my pressure is starting from 10 and it's going down to 4 or something other values, right? While conversion itself is varying between 0 to 1, and if I put it in the percentage form, it will vary from 0 to 100. So in that case my two scales are not aligned, and if I will put it into the same graph, one plot will go down while other will take the coverage part, right? So which we don't want. But at the same time I want it mechanism by which I want to see the variation within the same graph. I don't want them side by side. So in that case what you do is, within one graph we create the two separate y-axis, right? We have done it in school in our engineering problems also. So there we do it manually. We create one axis, left hand side, which represents your one y-axis, right hand side will represent other y-axis, right? And then you plot it accordingly, right? Your x-axis will become same, that will be a common axis, but your y-axis are different. So left scale is different, right scale is different. So I want to do that so that I can see at a one point I can take out the both data at a given volume, what is the pressure ratio and what is the conversion ratio, right? So for that we can use the Matlab to create that kind of plots, okay? So for that what you have to do, Matlab has this command which is y-axis, right? Create chart with two axes, okay? So let's look at the example here. If I do help y-axis, it creates charts with two y-axis. Y-axis left creates an axis that has a y-axis on both the left and right, or if an axis already exists, then this command activates the side associated with the only left y-axis, right? So what I will do, you can see the documentation part also. I'm just directly showing you right now. I do y-axis, I do left, okay? So I'm selecting to plot this on the left side, then I do y-axis, plotted this on the right side, okay? And this is done. Conversion, or just I can write simply XA, that is better, XA. Now this Y label should correspond to the left part, right? So I am putting it here. For the right axis I will have y label p by p naught. Okay, and let's run this. So you can see now I have two separate left and right y-axis, right? So my x-axis is common for both, which is volume, but my left axis contains the conversion xa and my right axis contains the ratio. Now they are on the different scale, so you can see it's more zoomed out compared to the previous part, right? And if I want, I can, instead of the ratio, I can put the pressure values also. So I will see the variation in both of them without them affecting the each other values, right? Each other plots. And then at 250 you can take out what is the conversion, what will be the ratio of the pressure value. You can further beautify this graph by adding the changing the thickness of the plot, changing the line size, right? So for the reference code that will be given to you, it has this variations, right? So if you use the GCA part, so GCA is used for the graphical customization in your plot, right? So here you can see I have control the font size, line width, etc. Okay, that you can try it out. Just play with this command search. I recommend searching more documentation part for the customization of the Matlab plots, right? Right now these plots are very basic, and since we want to understand it, I'm not putting too much thought into the customization. But if you want to do it, you can look at the various examples also. That will help you to, you know, kind of gain the idea on how to beautify the plots. Because coding something is fine, but when you are representing that data should be represented in a nice way, so that it's easier for other person to understand also, right? But that task I'm leaving on you guys. If you have doubt, do let me know, then we can take some example where we create much customization in the plots, how to create customization in the graphs, right? So we have completed task 1, where we wanted to see the change in the conversion and the pressure ratio with respect to volume. Now we have to compare the exit conversion with the case where no pressure drop is there, or where the pressure drop is neglected, right? So if pressure drop is neglected, so in our equation, right, if I ignore the pressure drop, so if I don't consider the pressure drop, then P and P naught become same, so this term will go away, but still my CA will remain same. Okay, my CA is same, only P by P naught term is not there. Okay, rest of the equation, this equation will also remain same. If I don't have change in the pressure, then my second differential equation dP by dV, this should not exist, right? Because since pressure is not changing with volume, this dP by dV will become 0. Now in order to do that, rather than creating a new equations, okay, since I will have only one equation, that is the equation 1, right? Rather than creating separate function or equation for that, I will just take the beta 0 value as 0 to find out what will happen when I don't have a when I don't have a pressure change. Okay, so this is my part 1. Now with change in pressure, part 2, which is without change in pressure. I will call the same ODE, extract out the same information, just I will give it them a different name, right? So instead of beta 0 here, I will put the value of 0. Okay, so that second equation itself becomes null. Then my XA without pressure change, okay, I am writing it as WPC. My pressure, okay, I don't have to take the ratio anyway, it will be 1, right? So let's run it and see. So if you will see, you have this XAWPC change with respect when your pressure is not changing, so you are going conversion till 0.6750. Compared to that, if you have pressure also changing and conversion is not that much, it's only 0.492. Okay. The pressure value without pressure change, obviously it should remain constant, so you have 10 10 10 value throughout, right? Now I can put this into the same plot, right? So my left axis, to see the conversion part here, XA without pressure change. Instead of blue, let me put it as K with dashed marking. Okay, Y label is already there, so I don't have to put it in, and run it. So this is how your plot looks like. So your conversion when the pressure is changing, and conversion when pressure is not changing. Okay, I can put a legend here also, that my legend becomes, so first I am putting XA, then is my P by P naught, then I have XA without pressure change. Oh, sorry, the notation XA. Oh, I think I have to put first left axis value first, and then this. Okay, and let's run it. So this is how you can see the variation. Okay, so this was part for the PFR problem, unsteady state PFR problem. Now let's move forward with the last example. It's a fairly small example, and then I will end a note with a question. Based on that, we will move forward with the for the next class, right? So now problem 4 is co-current heat exchanger design. So you are designing a double pipe heat co-current heat exchanger to cool a hot process steam with a cold coolant stream. The information is given as stream H is a oil, which flow rate is given, inlet temperature is given, heat capacity is given. For cold stream also same information is given. Your exchanger details are overall heat transfer coefficient U, which is 350. Now this is heat transfer area per unit length. So instead of giving total area, you have been given heat transfer area per length, so which is 0.2 meters square per meter, and length of your heat exchanger, which is 10 meters, is given. Right? Now if you will try to solve it, like what have you been asked first, let's look at that. We have been asked to determine the outlet temperature of both stream and the temperature profile along the length of exchanger, right? So if only outlet stream, the first part was asked, then it's just solving a normal heat balance, right? You can do it, your Q is equal to UA delta T, and then that U becomes MCP delta T, right? So if you solve these equations, you will find the value of your outlet temperatures. But you have been also asked that along with that, you have been asked the temperature profile along the length of exchanger, right? So as you are moving, since it's a co-current exchanger, both hot and cold streams are coming in one direction, and as you move forward in the length of your exchanger, your heat exchange will take place, and your the temperature of both the stream will vary. So you have to see how that change is being seen, and lastly you have been asked to find the heat transfer rate. Okay. Now for this part, to see the variation of temperature with respect to length, I can do this energy balance equation. Like if I consider any stream, let's say I'm considering hot stream, so it's change in the energy that is given by MCP delta T. So this will give you the energy required to change the delta T temperature of your stream, right? That heat transfer rate since it's mcp delta t, that rate will be exactly as heat transfer that is happening between your hot and cold stream, right? So if this is a hot stream and its temperature is going down, that energy is transferred to the cold stream, right? And that is given by ua delta t. Now here this a is total area, but if I want to write it in terms of the area per length, what has been given to us, right? We have been given as area per unit length. So instead of a, I can write al into dz, which is like, if I'm considering small fraction, I'm considering small, this is my big pipe, I'm considering small fraction delta z. I know what is the area per length, so I multiply area per length into this dz part, so I will find the total area for this small portion. Okay, so this is that what equation denotes. Now if you rearrange it, then you can find change in temperature with respect to length dz is given as ual th minus tc divided by mcp, right? So this is your equation. Now you have two stream, one is cold, one is hot. So for both, if I consider the cold stream, my mcp will include the cold stream flow rate and cold stream heat transfer coefficient value. If I consider dth by dz, my m and cp are for the hot stream. But here one thing you observe, that for the hot stream I have written the negative value. Why? Because see, this is the same energy which is being transferred from hot to cold. Now cold stream, its temperature will increase, so dt by dz will be a positive value, while for the hot stream its temperature is going down, should be the negative value. So this will be the decreasing slope, right? Sorry, decreasing value. So that's why you have a negative slope, that's why the negative sign comes here. Okay, so for this problem, so it's a simple heat exchanger problem which we converted into the ordinary differential equation form to see the temperature variation with respect to z values, right? This we have done. Now we have two ODEs. So two ODEs, one TC, one for TC, one for TH, which involves one independent variable z, right? I know the initial value problem. So this is ordinary differential equation, and I also know this is initial value problem. How do I know that? Because it's a co-current heat exchanger. That means since it's a co-current heat exchanger, both the hot and cold stream are entering at L equal to 0, okay, or Z equal to 0. So at the start of your heat exchanger, both the things are coming. So you know the temperature of hot and cold stream at the inlet. So this becomes ordinary differential equation initial value problem, right? And we have been solving this, right? So in the interest of time, what I will do, I will not completely code it, but we'll go through the reference example. So here it's a co-current heat exchanger problem, right? We have been given data. So you have hot stream data, its flow rate, its CP value, its inlet temperature, cold stream data, flow rate, CP value, inlet temperature, exchanger data, right? So same information that has been given here, we have translated it. Now this equation, this 2 ODE, since except TH and TC, all the other parameters are constant. You can refer, I am referring it as a constant alpha and beta. So that's why I have two constant alpha and beta. So alpha is UA by MHCP, which is for hot stream. Beta is for UA by MCP for cold stream, right? So I have computed alpha beta. My two equations becomes dTh by dz, dTc by dz, and I am creating heat exchanger ODEs which are function of z and y, right? And for that, see, only thing you need is Th minus Tc value. So Th minus Tc is given, your y1 represents Th, y2 represents Tc, alpha and beta constants are given. So this creates your ODE function, right? Now to solve the ODE problem, your span is from 0 to L. Your L is 10 meter, which is heat exchanger length, right? Your y0 value, initial value, you know the inlet temperature of hot stream, you know the inlet temperature of the cold stream. you call a ordinary ODE solvers, right? ODE-45 we are using extensively. You call it, you call your heat exchanger ODEs, your span, your initial value, and it will give you the TH and TC data, and then at the end it's plotted, right? So if I do that and run it, this is how it will look like. So my inlet temperature, both I knew that cold stream was at 25, hot stream was at 120. With length, we are observing the evaluation that they are both decreasing, and okay, the hot stream temperature is decreasing and the cold stream temperature is increasing, and this is how the co-current heat exchanger temperature profile looks like, right? It's a parallel flow, so this is how it changes. What else we have been asked? We have been asked compute heat transfer rate. So that is nothing but you can take it as your overall heat transfer is mCp delta T, right? So you know the flow rate M, Cp for the hot stream, inlet of the hot stream minus outlet temperature of the hot stream, and outlet temperature is given as end value of your TH and TC computed from your heat exchanger data, right? So what is this value? So your outlet temperature, hot outlet temperature, from 120 it goes down to 106. Your cold stream temperature, it increases from 25 to 34 degrees centigrade, and overall heat transfer is this 58.05 kilowatt, right? So this was one example. Now it's very if you will think about it, compared to other example, it's very straightforward, right? Now the question here that I want to ponder is that since it's a co-current heat exchanger problem, we solved it very easily. We converted into the ordinary differential equations with respect to Z, the change in temperature with respect to Z. We knew the initial values, and when we solve it through our ODE solvers, initial value problem solvers, right? But what will happen if instead of co-current we have a counter current heat exchanger, right? So can you think about it, what will happen? So here what is happening, that so here what is happening is that you know both the value of cold and hot stream at Z equal to 0, okay, which is needed for our ODE-45 solver. You need the initial value to start the solver. So what this ODE initial value problem solvers are doing, the Euler's method or RK method that we have done, that we start with the initial value based on the model that you are using, either be Euler's or the RK4, right? You move in the next step based on the previous step data, right? So you are moving forward in the independent variable direction, right? So here in the direction of Z, based on the value of TH and TC at Z equal to 0, I am moving ahead with the value at Z is equal to Z0 plus delta Z, right? So we are moving forward in the direction based on the initial value. But let's say if it's a co-current, right? So I have one data here, like I know hot stream is coming at hot stream is entering at the inlet of at Z equal to 0, while cold stream is coming on the other side, right? So here in that case, this 25 value will come here, right? So one is decreasing and another, so this time profile will change, okay? So that is fine. We know it from our experience by learning heat transfer operations, right? That how will profile look like in the counter current operation. So in the counter current operation, 120 it will start and it will go down. Your cold stream is entering at 25, it will go up in this direction. But now in order to solve this, this problem has become something else, because in ODE-45 what I needed to do was I needed to know the initial value at Z equal to 0, but now I don't know the value of Z value of TH and TC at Z equal to 0. I only know the TH value at Z equal to 0. TC value is known at Z is equal to L, right? So my question here is, what kind of problem now we have created, right? It doesn't appear to be initial value problem. I don't know the initial value of TC at Z equal to 0. So in that case, what will happen? How do I solve it, right? So that is something for you guys to think about. We will pick this question again in the next class, but instead of co-current, we will think about what happens when we have the counter current example, right? In counter current, how do we solve it since we don't know the initial value, right? So what kind of problem we have created and how to solve it, that will be the agenda for the next class, and accordingly we will move forward, right? So I'm ending the class now, right? Thank you for joining.